All right, let's go ahead and get started on Chapter 4. We're going to continue talking about linear programming, and we are going to introduce a concept known as sensitivity analysis. So, what is sensitivity analysis? Essentially, sensitivity analysis asks the question, what if? All right. It links the outcomes and the conclusions to our initial assumptions about the model. All right. And what happens is it involves changing one or more of the variable values to see how the outcome, the objective, changes. Okay, so think about varying an interest rate, or think about any of the problems that we have done. If you were to change any of those decision variables that Solver has been doing for us automatically, if you were to change any of those, you would see a difference in the objective. Okay, so in essence, using Solver to find the best possible value for an objective is just another way. It's an automated way of performing sensitivity analysis. All right, it does all of that. It's not exactly I've been calling it trial and error. Because if you had to do it by hand, that's probably the way you do it. It's not really trial and error. It is based on mathematics, but it sometimes helps to think of it that way. Solver does that trial and error, does that sensitivity analysis for you in those yellow cells in order to find the best possible objective, whether it's a maximum or a minimum. All right. So, in a way, we've been doing sensitivity analysis all along. But we're going to, in this chapter, we're going to take a different approach to sensitivity analysis. Rather than changing the decision variables, which is what we let Solver do, we're going to change some of the other data, the other parameters of the problem, and see what happens and record the results. So we're going to look at changes both in the objective and in the optimal set of decision variables. As I've already said, sometimes you're going to run Solver and you're going to get a result and you're going to say that's not acceptable. All right. And so sensitivity analysis allows us to play around with some parameters to see if we can change the rules, if you will. So we're going to look at three different things specifically in this chapter. One is we're going to introduce Solver Sensitivity, or the Sensitivity Toolkit. This is an add-on that you will download and install in Excel that the author of the text has written, and it's a very powerful, very handy tool. We're also going to look at the sensitivity report, and this is a report that is available when you run Solver. We haven't looked at it yet, but it's always been there. And then finally, we're going to look at patterning. All right, and this is actually a way of doing a sensitivity analysis by hand, essentially, not using any Excel tools. All right, and you might be thinking, why on earth would we do that? Because it sounds hard, and actually it can be a little bit complicated. But if you learn to do the patterning in a model, you'll actually understand the model a lot better. So again, why? Why do we do this? We have our data, we run Solver, we get a solution, right? Why fiddle around with the parameters? Okay, good question. One, parameters are not always 100% accurate. There is some variability, and so we might be able to take advantage of that, or we might be able to prepare for that. Our solution may be more sensitive to some parameters than others. Okay, and so it's helpful to know that if we change one thing, the objective changes a lot. If we change a second thing, it doesn't change quite so much. Our optimal solution may be satisfactory, and I have already talked about this one. Just because you get an answer doesn't mean you have to implement it. It doesn't mean that you want to implement it. And if that occurs, then we've got to start looking for ways of changing the rules. So solver sensitivity. You're going to get a chance to look at it as we go along here, but it is similar to Excel's data table. If you've ever used Excel's data table, that is a way of doing sensitivity analysis. It allows us to vary one or two at most parameters over a predefined range, and we also get to define the incremental change. And although it's possible to vary two parameters at a time, the results don't usually tell us as much as if we vary one parameter at a time. So we're going to focus on varying one parameter at a time. So let's take a look at how it works on a model that we have already solved. So you remember Goodwin Manufacturing, all right, and this was a classic transportation model, all right, and we've already run Solver, all right, and we've gotten a result. So we see the in the yellow cells we see our solution, okay, and so these are the best routes that we can take that will meet demand, stay within our capacity, and minimize our cost, which is our objective. All right. But let's say that some of these parameters are negotiable. All right. So let's say we want to vary the Pittsburgh, the value of Pittsburgh to Atlanta. And we want to see how our results will change as we vary from 25 cents to 75 cents per mile. Suppose we have an opportunity in some way of negotiating this rate down. Maybe we negotiate with the shipper or whatever. Okay. So we would first of all we have to have got this model already set up and run solver on it. Okay. And so now we can run solver sensitivity. All right. And so we identify, first off, in solver sensitivity, we identify our objective function. We identify any other cells that we might want to record, and then we choose the type of table. And as I said before, we want to do one-way tables. All right, those are the most useful. Okay, so our objective function is C17, and we want to take a look at how our optimal solution from Pittsburgh changes as we vary this cell right here, 36 cents. We're going to vary that from 25 cents to 75 cents a mile. All right. So continuing on, we have to, in solver sensitivity, we've clicked next. We need to choose the cell to vary. All right. This is the one that's going to change. We choose the input type. All right. And again, for our purposes, we're always going to choose the default, which is we choose the beginning and the end and the increment. All right. And then we input the first and the last values and the increment value. So we're going to vary from 0.25 to 0.75 in 5-cent increments. Okay. Then we click finish. And so here are the results. Now, one of the things that you're going to notice is that solver sensitivity doesn't always format your headings here very good. All right. So what I've done up at the top here is added a little bit of formatting just to show you what we're seeing here. This is the route PA, PB, PC, and PD. These are the other cells that we told solver sensitivity to take care of. Okay, so this is the result. All right, from 25 cents to 70 cents, we can see how the objective changes, right? And obviously, it as the cost per mile goes up, you very naturally see that our total cost goes up as well. That makes sense, right? And so we'll talk about some of these other parameters, but right now we're just going to focus on these two. So here are the results of the solver sensitivity, and they've been formatted a little bit to make them more understandable. Okay, I've got the thing that we were varying, the route from Pittsburgh to Atlanta in yellow, and the objective, the thing that we are trying to minimize, in green. Okay, the rate of change. Notice that it starts to decrease as we go up in price towards 75 cents. The rate of change is simply this value minus the previous one divided by this value minus the previous one. Okay, so it's the change in objective divided by the change in the variable that you are varying. All right, and so this can be advantageous, as you can see. Once you get to 75 cents, the rate of change drops to zero, and so if you go higher than this, there will be no change in the objective at all. The base case is, if you remember, if you want to look back, what we ended up with is sending 5,000 from P to A and 10,000 from P to B. All right. And so what I've outlined here is what's known as the base case. Essentially, anywhere from 30 cents to 35 cents results in the result that we ended up getting with solver. Okay. And so that can be useful. So as you see, once you get to about 40 cents, then the PC route becomes more attractive, and you start taking less from the PA route and putting more into the PC route. And as you can see, as it goes along, once you get to about 65 cents, the PA route is completely unattractive, and we don't use it anymore. So this can be important. All right. The optimal solution is sensitive to the PA price. All right. So it is a point that seems to be worth negotiating. All right. But keep in mind that when you change the PA price, it affects the other routes. All right. It doesn't just affect what you send through PA. Okay, so we can do finer increments. For example, we can do 1 cent. All right. And so this gives us a little more insight. We can see that the base case actually holds for 27 cents all the way through 32 cents. Okay, so all the way from here up to here, the base case holds. All right, actually 37 cents, my mistake, all the way up to here. Okay, and then after 37 cents, that's when we start to get different alternatives. So this is known as the range of insensitivity. Okay, so our base case is insensitive between 27 cents and 37 cents. It won't change. So there are three patterns to observe in this data. And as I said at the beginning, I want us to look at patterns. All right. So that we're not just plugging in numbers, pressing a button, and getting a result. It's really important that we understand as much as is possible what's going on here. Okay. So, first thing, when a coefficient becomes more attractive, the corresponding variable will increase or stay the same. So when the PA price becomes more attractive, in other words, as it drops, the corresponding variable, the PA variable, what's outlined in red here, will increase or stay the same. That makes sense, right? As the route from from P to A becomes less costly, we're going to send more along that route. Okay. The optimal value will also improve or stay the same. It will not drop. Okay. And also notice that the change does not need to be gradual. As new routes become more attractive, okay, suddenly you have kind of big lurches. All right. So we go from, if we start at 75 cents and start reducing the price, we go from 0 and we jump all the way up to 2,000. And then we stay at 3,000 for quite a while, and then it jumps to 5,000 for a couple of iterations, and then to 8,000. So this is not linear, it is not gradual, okay? And that's because we aren't just looking at PA. As we change these prices, the other routes come into play here. So let's take a look at Goodwin Manufacturing again, but instead now of changing one of the price parameters, we're going to change one of the constraint parameters. All right. The Pittsburgh capacity is a scarce resource. We max it out at 15,000. So what we're going to try and do is we're going to vary this right-hand side parameter from 14,000 to 24,000 in increments of 1,000. All right. And we're going to see what this will get us. Okay, and now again, I've reformatted these results a little bit. It's usually a little bit uglier, the report that comes out of solver sensitivity. All right. But notice that the rate of change is on a very different scale. Okay, but again, it is still calculated by the change in objective divided by the change in the variable that you are changing. Okay. However, for scarce resources, the rate of change is the marginal value. We've already talked about marginal values, but now we're going to give it a new name. It's known as the shadow price. Okay. Back in the previous homeworks, when you increased the value of a right-hand constraint by one unit, and you reran solver, what you were essentially finding at that point was the shadow price. This is the marginal price of a 1 unit increase or decrease, if you will. Okay, so that can be very handy. All right, and notice that as capacity increases, we end up with an objective that continues to go down to a certain point, and then at a certain point, it is no longer valuable. All right, and so there is no point in putting money, for example, in increasing capacity past 20,000 because it's not going to get you any further increase in profit. Okay, now let's take a look at this from the perspective of Brown Furniture. All right, we're going to explore a change in chair profit from $15 to $35. We might be able to do this by negotiation with our raw materials supplier, or by changing our processes or something like that. Okay, I've run the results, and so what we've got is the chair profit goes from $15 to $35, and notice that the objective does not really begin to change until you get to $22. So between 15 and 21, we have no incentive to build any chairs at all. And if you recall, our optimal solution did not include any chairs. And so from $15 to $21, our base case is insensitive, all right, to the change in chair profit. But once you get to $22, you start thinking, oh, you know what? I should build some of these chairs, okay? And notice that we start building chairs and we stop building desks, all right? And that continues on till you get about to $32 of profit. And then we decide to put all of our resources into chairs, okay? So it's not consistent all the way through, but that's okay. We don't expect it to be gradual, as I've said before. So here we look at Brown Furniture again, and we do it by exploring the sensitivity of the machining hours constraint. And we vary it from 1,200 to 2,000 in 50 unit increments. And so as you can see, the objective increases for a certain time, and then it just levels out. The rate of change gradually goes down and it levels out. So as we saw with a previous example, a scarce resource, the less you make it scarce, the less value it has. So if we look at it in graphical form, we can see that as we increase the machining capacity, essentially we're loosening that binding constraint. That profit will go up rather sharply, and then it will start to taper off, and then eventually, a little over 1800, it will level out, and it will no longer be a scarce resource. So now let's take a look at the sensitivity report. All right, so we're going to leave solver sensitivity behind right now, and these can be a little bit confusing, so you'll probably mix them up in your mind a little bit. But one is solver sensitivity, and one is the sensitivity report. So the sensitivity report is a function of solver. All right, and when you get that message that says solver found a solution, you have the ability to select the sensitivity report, click OK, and you get the sensitivity report. It appears in a new tab in your worksheet. So if we look at the Goodwin Manufacturing sensitivity report, this is what it looks like. On the top, you have the variable cells, okay, and we have a number of different columns. We have the final value, reduced cost, objective coefficient, allowable increase and decrease, and then at the bottom we have the constraints, okay, and their name, the final value, the shadow price, the constraint on the right hand side, and the allowable increase and decrease. And we'll talk about these things. So here is the sensitivity report for Goodwin Manufacturing. So, and this is the top of the sensitivity report that outlines the variables. So what do we have? We have the values. These are the decision variables and their values that solver comes up with for our optimal solution. Okay, we have our objective coefficients. These are essentially the costs that are in the cost matrix in our transportation example. We have our allowable increase and decrease. Okay, in a lot of ways, the sensitivity report could be alternatively known as the insensitivity report, because what it tells you is how much any of these values could change before it changes the base case, before it changes the optimal solution. Okay, so for example, the price could increase from Minneapolis to Atlanta basically forever, and the solution would not change. However, if the Minneapolis Atlanta route reduced in price by more than 28 cents, suddenly the MA route would become attractive. Okay? And so that is essentially the allowable decrease is really essentially the same as the reduced cost. Notice the reduced cost only appears as a positive number for those routes that don't get taken. Okay, so the way to interpret this is that Minneapolis Atlanta is not going to kick in and be used unless the cost goes down by at least 28 cents. Minneapolis Boston is not going to kick in and be used unless the cost goes down by more than 30 cents. Same for Minneapolis, Denver, and so on. So this is the range of insensitivity. Okay, the sensitivity report is not as flexible as solver sensitivity, but it is more precise. So here we have the sensitivity report on the constraint side for Goodwin Manufacturing. All right, so this is the lower half of the table. All right, we have the constraint cells, their names, the final value. This is essentially the left-hand side values that solver comes up with. We have the shadow prices. These are the marginal values of the constraint. So this is the value either in increased profit or reduced costs based on the movement of 1 unit of any of the constraints. We also have the allowable increase and decrease. This is essentially the range, the insensitivity range for these constraints. So for example, for Atlanta, all right, we have a demand of 8,000, all right? And so that demand could go up to 11,000 or down to 7,000, and that shadow price of 65 cents would still hold per unit. All right. And the sign of the shadow price indicates the direction compared to the objective. Okay. So in this particular case, if we increase demand, we also increase our cost. All right. That's our objective in this case. If we increase capacity, we reduce our costs. That's why there's a negative sign, because they move in different directions. So, brown furniture. Let's take a look at brown furniture. Okay. The variable cells are up there. This is the whole sensitivity report. All right. We have our final values of 0, 160, and 120. We have our reduced costs. And so our objective coefficients, our allowable increase, and our allowable decrease. Okay. So in other words, profit has got to go up by $5. All right. Before chairs becomes viable, before it begins to be noticed by solver. All right. In the at the bottom, we have our constraints, we have our final values, our shadow prices, and our right hand side allowable increase and decrease. So we can see that since there are only shadow prices for assembly and machining, they are the only ones that have value. Therefore, they are the only ones that are scarce resources. Okay, so how do we compare solver sensitivity versus the sensitivity report? Well, one thing, as I said, solver sensitivity is more flexible. Okay, you have more ways of looking at things. The sensitivity report is more precise. Solver sensitivity describes the sensitive and insensitive region, whereas the sensitivity report only describes the insensitive region. So it'll give you a range of how far you can go up or down before something changes, but it doesn't really tell you what's going to happen when you get to the change point. All right. Solver sensitivity can vary two parameters at once, whereas the sensitivity report can only tell you what's going to happen one at a time, if you vary things one at a time. Solver sensitivity is less sensitive to the spreadsheet layout than the sensitivity report. The sensitivity report works best when you follow the formal layout we've been using. Okay, and that's one of the reasons why I'm kind of a stickler for the layout. Okay, I have students every once in a while that kind of rebel a little bit and say, what does it matter how I lay the model out as long as I get the right answer? Well, as I've been emphasizing all along, this is much more than just getting the right answer. The sensitivity analysis is important. But even if you didn't do sensitivity analysis, a well laid out model is easier to understand, it's easier to interpret, it's easier to provide some strategic value. All right, let's talk about a condition known as degeneracy. Sounds kind of serious, doesn't it? All right, let's take a look at Goodwin Manufacturing. This is our original model, okay? And some things I want you to notice about the constraints portion of the sensitivity report, okay? All allowable increases and decrease values are non-zero, okay? So what that means is that the shadow prices hold in both directions. All right. So we can have some increase or decrease on all of the constraints, and the shadow prices will hold. All right. So this solution is considered non-degenerate, and that's a good thing. Okay. We can be confident now that we can make decisions on whether to put money into some of the constraints, okay, to loosen them, to try and achieve a better objective, and that we can go in either direction. All right, and so this is a good solution. Now, let's take a look at Goodwin Manufacturing, and the Minnesota capacity has increased to 12,000. All right. So now take a look at the report and you should see that things have changed a little bit. All right. The some of the allowable increase and decrease values are 0. This is known as a degenerate solution. Now, it's not the end of the world. Calling it degenerate makes it sound really bad, okay? It's not really bad. It's just you have to use a little bit of care here because the shadow price does not hold in both directions. Okay, so for example, for Chicago, we can decrease the right hand side in Chicago, and it will be worth 27 cents per unit. All right, but we can't increase it. We don't know what will happen to the shadow price if we increase it. If we add one more unit, 12,001 at Chicago, we're going to get a different shadow price. We're at a boundary. Okay, the solution will degenerate at this point. We are at a boundary. We're actually at two boundaries in this particular case. So let's also take a look at something known as alternative optima. And I've spoke about this already once. But the fact is that when we run solver, we get a solution that provides the optimal objective. Okay. But there are times when there are different sets of decision variables that will produce an equally optimum objective. Okay. And so sometimes there is some flexibility. First off, we have to assume a non-degenerate solution. Okay. That is where the shadow prices hold in both directions. All right. Take a look here. All allowable increase and decrease values are non-zero. All right. What this means is that our optimal solution is unique. Okay. In other words, our solution is going to hold in both directions for any changes in our objective coefficients within these ranges. Okay. This means we have a unique solution. All right. There is no other combination that will produce the best solution or an equally best solution. Now, if we raise the PA price to 38 cents, what have we got here? We still have to assume that our solution is non-degenerate. Our shadow prices are still going to hold in both directions. All right. But now notice that some of our allowable increase and decrease values are 0. All right. This means that there are alternative optimal solutions. Okay. And so that means you might be able to tweak things just a little bit, tweak the coefficients just a little bit in one direction or another and get an equally optimal solution. Maybe you want this, maybe you don't. Sometimes it's nice to have some variability or some discretion on your decision variables. Now, this is where we have a little bit of fun, all right? Although my definition of fun and yours might not be the same thing. But we're going to take a look at patterns in linear programming. This is where we stop relying on solver, okay, and solver sensitivity, and we start looking at the models ourselves, okay? So patterning seeks insight rather than solutions. We're still going to use solver to give us solutions. But after we've done that, we're going to look at the solution and try and gain some insight. All right? And one of the ways that we're going to try to achieve insight is to look for a qualitative pattern in the optimal solution. Patterning allows us to understand what if type questions without rerunning solver. Okay? And people, again, might be asking, why would we do this? We have solver. We can just rerun it. But it's always better to understand than to simply let the machine do your thinking for you. Okay, so how do we do patterns? How do we figure out patterns? First thing that we do is we look for two things after we've optimized a solution. We look for binding constraints and we look for non-zero variables. Any constraint that is not binding is no help to us. Any variable that's not used is no help to us. All right? From this, we can create what we call a structural scheme. All right? And then we can translate the structural scheme into a computational scheme. All right? And this allows us to vary the parameters and construct solutions without solver's help retrospectively. By that I mean we have to run solver and get a solution first before we can look for a pattern. Yeah, it sounds a little bit crazy, but yeah, hopefully you'll see the value in it. Okay, so here's our Goodwin Manufacturing Transportation Model, and let's see if we can figure out the structural scheme. Remember that we want to look at binding constraints and non-zero variables. All right, well, we know that all demand is binding. All right, what we receive at each location is the same as the demand. We know that the Minneapolis and Pittsburgh capacities are binding. Everything that they can send out, they send out. All right. We also know that we have 6 desired routes. Those are the ones that are non-zero. All right. So now what do? Now that we've identified those, we have to identify what we call our first priority routes. And what that means is first priority routes are where all demand is met by a single source, or a single source sends, or a source sends all of its capacity to a single destination. So if you look down here, okay, you can see that because there's only one value in the Boston column, all demand is sent from a single source, from Pittsburgh. Jump over here for Denver. Everything that Denver gets is sent from Tucson. So those are first priority routes. Also, if you look horizontally, Minneapolis to Chicago is a first priority route because Minneapolis sends everything it's got to Chicago. Okay? So those are our first priority routes. And now once we've identified them, it sometimes helps to block them out so they're no longer in your field of vision. Okay? Because really what you're looking for are values that are alone in either the column or the row. Okay? So now that we've blocked those out, we can look for second priority routes. And we do the same thing. We look for any place where demand is has a single value alone, and where capacity has a single value alone. And we just pretend those things that are in red don't exist anymore. So now we can see that Chicago is entirely met, or at least the rest, from Tucson. All right? So Tucson, Chicago is a secondary route. Also, Pittsburgh is going to send the rest of it, what it has, to Atlanta. Okay? So Pittsburgh, Atlanta is a second priority route. So we identify that. All right? And now we can block those out. That only leaves Tucson, Atlanta, so that is our only third priority route. Okay? So we identify first priority routes and second priority routes, and then third. And if it goes on from there, but typically first, second, and third are about all you get, at least with the size of the models that we're working with. Okay, so now we have our computational scheme, and take a look and see how it works. Don't be afraid to backtrack a little bit and watch this again, okay? You need to get your head around this. So now we have our first, second, and third priority routes listed, all right? So PB is a first priority route. The shipment is 10,000. TD is 9,000. MC is 10,000. And so you can get these values right out of the solution. Okay? This is our computational scheme. let's take a look at it in a little more detail. And so let's try talking this through. All right. So PB, the route PB, all right, Pittsburgh to Boston, is determined by the Boston demand. Okay. Pittsburgh could send more, but that's all Boston wants. So that value is determined by the Boston demand. Likewise, TD, Tucson to Denver, is entirely determined, that amount is entirely determined by the Denver demand. Okay? MC, on the other hand, Minneapolis to Chicago, is entirely determined by Minnesota's supply because Minneapolis, because Minneapolis sends everything it's got to Chicago. All right? So we've switched from vertical to horizontal. All right? Now, PA is a second priority route. It is determined by the remaining Pittsburgh supply. We sent everything that Boston wanted, we sent. Then we sent all of the rest to Atlanta. Okay? Tucson, Chicago is determined by the remaining Chicago demand. Chicago took everything that Minneapolis could send, but it still wanted more, so it got it from Tucson. And then finally, Tucson, Atlanta is determined by the remaining Atlanta demand. Atlanta got all of the rest of what Pittsburgh had available after Pittsburgh supplied Boston. All right, but it still had some need. Okay, and so it got it from Tucson. All right. Again, go back over this. You'll see that this works, and you'll get a feel for how this is done. So, the whole point of these patterns, of doing these patterns, is to be able to answer what if questions without using solver. So suppose we raise Boston demand by 500. Okay? So take a look. We've done a little bit of spreadsheet magic here. All right? Now we know that Boston was entirely supplied by Pittsburgh, right? So if Boston demand goes up, all right, then we know what the cost is, okay, because we know what the Pittsburgh Boston cost will be, all right. But that means that Pittsburgh now has 500 less to ship to Atlanta, all right. And so that's a negative cost, all right. Whatever we would have sent to Atlanta at that price is now gone. That means that Tucson has to step up and supply 500 more to Atlanta because the Tucson capacity is not binding. It has extra capacity. That gives us, so the Tucson Atlanta route is going to cost $325. Do the math, and it ends up at $295. Divide 295 by the 500 units, and that is 0.59. That is our shadow price. We just figured out our shadow price without using solver. Okay? Does that make sense? Go ahead and go back over this again, and you'll see how it works. Now, the question is, how long will it hold? Okay, well, we know that there were 1,000 units in excess capacity in the system. Tucson had 1,000 unused units in this system, okay? So that is how long this will hold. So let's take a look for a pattern in the product portfolio problem, all right? Product portfolio problem asks the question, what products should we be dealing in? All right, whether we make them or buy them. General Distributors is a vegetable distribution company that distributes to grocery stores, frozen foods. All right, so what we have here is 15 vegetables, frozen vegetables, that they deal with on a week-by-week basis. The minimum and the maximum values in the data table is their forecast. Okay, We also have their price and their cost so we can figure out profit. And in fact, in the objective row, we have calculated profit. So obviously we have to purchase at least the minimum, all right, and no more than the maximum, all right. We also have constraints on credit line that we can use up per week, and we have a space restriction, all right. And that's the amount of space that is taken up. Each carton is 1.25 cubic feet of space. All right. So let's take a look at patterns here. One thing, we always look for binding constraints, and we see that the credit constraint is binding. All right. So we need to take note of that. The space constraint is not. We've got space to spare. Now, we have 4 vegetables that are purchased at their maximum. Everything else but one is purchased at the minimum. Okay? The one is lima beans. Oh, lima beans. Okay? Anyway, lima beans is purchased somewhere in between the minimum and the maximum, and that is the only one. And you'll see why as we go along. One of the things that will help us make our decisions is the calculation that you see at the bottom of the screen, and that is the profit to cost ratio. What we have done is we have ranked these vegetables in terms of their profit to cost. In other words, if we have any decision at all to make, we want to make the one that makes us the most profit. Okay? So let's consider these. All right, so what is the computational scheme that we used for the previous problem? First, we must purchase enough of each product to reach our minimum. All right, that's absolute. That's first priority. Now, we want to rank our products by profit to cost. Okay, and then starting with the most profitable product, we purchase each at its maximum until the credit limit is reached, because that is our binding constraint. And this happens when we get to lima beans. So we buy up enough lima beans until our credit limit is finished. Okay? So that's the computational scheme. It's a lot simpler than you might have thought by looking at the model. Purchase enough of all of them to reach the minimum. Rank the products by profit to cost ratio, and then we start with the most profitable product and purchase it until we reach the max, or until the credit limit is reached. And we do that with the second most profitable product and so on. And in this case, when we get to lima beans, we run out of money. So, add a carton of squash. All right? Who wants squash? Especially frozen squash. Come on. Anyway, we add a carton of squash. So what will happen? Well, squash brings in a profit of 20 cents. All right? But we have exceeded our credit limit, so we have to remove something. All right? Now, most of our products are at their minimum, so we can't remove any of those. All right? So we have to remove the least profitable product that isn't at its minimum, and that's lima beans. Squash, lima beans, not much of a trade-off. Okay? Well, squash costs $2.50. Lima beans cost $2.80. So we remove 2/5 divided by 2.5 divided by 2/8 worth of lima beans, about 89 cents worth. Well, the lima bean profit is 33 cents. So the loss of profit is 0.893 times the 33-cent profit. So we lose 29 cents of profit. Okay? So the overall profit decreases by the 20 cents we made from that extra carton of squash minus the 29 cents that we lost by reducing our lima beans. And so we are going to lose about 9.5 cents of profit by adding a carton of squash to our demand. All right. What we would have done there is added a minimum of 1 unit of squash. Now, how long will the pattern hold? This pattern will hold until either squash wheat reaches its maximum, or lima beans reach its minimum, or the space is reached. In this particular case, squash, the maximum of squash is what we reach first. Okay? Now, again, go back, follow this through. It makes sense, all right, but it takes a little to get your head around. The investment model. Okay, we've looked at this, right? This is the college investment model that we saw in the last chapter. All right, let's take a look and see what we can find out. All right, first of all, we are using balance equations, so that means all of our constraints are binding. All right, we also have a number of non-zero decision variables. So we have to take those into account. All right. Those are the two things that we look for. So we can ignore A1 through A4, A6, A7, A8, C1, and C4. They do not matter to us at all. So this is our flow diagram. And with the investment model, it helps to take a look at the resulting flow diagram and work backwards. So we can see that the year 7 requirement, $30,000, is met entirely by D1. Year 6 is met by B5. Year 5 is met by A5. Year 4 is met by B3. Year 2 is met by B1. And year 0 is met by our initial investment. Okay, so these are our priorities. All right, the computational scheme. All right, let's say that we increase the year in 7 requirement to $31,000. All right, the increase in investment is that $1,000 divided by $1.65. Remember that investment D gives a return of 65%. All right, so that 1,000 increase divided by $1.65, which is where it's met from, is $606.06. This is our shadow price, and this shadow price will hold indefinitely. Okay? Now, Delta Oil. This was a big one, and it was complicated. All right? But again, if you work through it, it will make sense, and go through it a number of times if you need to. All right. We've got a number of non-zero decision variables. In fact, all of them. We have a number of binding constraints. All of our balance equations are binding, okay? And two of our other constraints are binding: cracker capacity and demand for regular gas. Okay? So, we also have binding constraints for the regular and premium blend. All right. Yes, those are essentially equal because they're such small numbers. All right, they're as close to zero as makes no difference. So those are our binding constraints. Those are our non-zero variables. Well, let's take a look at the optimal pattern. The cracker is fully utilized. The sales potential for regular gasoline is fully realized. And the blending constraints for regular and premium gas are met. Okay, that is our optimal pattern. Now, suppose we can get 1,000 barrels more out of the cracker without altering the incoming feedstock and high-end product. All right, let's just suppose it's magic. All right. Let's follow it through. Since regular is already at its maximum, we don't need more catalytic regular. So the extra 1,000 goes to catalytic premium. All right. Since premium is 75%, 25% CP to BP, we need an additional 333 barrels of BP. All right. Which in turn means we need the same amount of blend and of distillate. All right. Crude is 60% distillate and 40% low end. Therefore, it must be increased by 333 divided by the 60%, or 556. 222 of which will go to low end. Is your head spinning yet? All right. 1,000 barrels of CP at 75%, 25% means an increase of 1,333 barrels of premium. Profit equals premium times 55 plus low end times 36 minus crude times 33 equals $63,000. Rounded, okay, the decimal points rounded. Therefore, our shadow price is 63,000 divided by 1,000. It's $63. All right, and this is represented by node 3 in the model. All right. Now, again, like I've been saying all along, go back, follow this through, look at it again. It's really just adding, subtracting, and dividing. Okay, but it's important that you see the pattern. All right. This is, and again, you might be saying, I'll never do this. All right. Maybe that's true. All right. But the more that you understand the model, the more that you look at it, and you're not just an automaton that's punching in numbers and hitting solve, all right, the better. Okay. This is going to help you in your decision making process, even if you don't realize it. Understand is always better than just punching buttons. So, in conclusion, all right, as I've been saying all along, optimization is more than just getting the right answers. It is about understanding the model. Okay, one of the ways that we can gain insight is through sensitivity analysis and patterning. Okay, allowing us to see the potential benefits or disadvantages of changing our parameters and under what conditions our solution holds. If our solution holds well in both directions, then it's a robust solution, and we have confidence in it. So insensitivity is not a bad thing. Okay, we just want to know how things change if we change some of the rules. That's it for this chapter. Go ahead and begin the homework, and we'll see you in the next chapter.